Okay, good afternoon, Professor. My name is TangHuyming, and this is my presentation for the second operating system project. The second project tackles the bounded buffer problem, and there are two versions of it. The one which simulates a race condition in the bounded buffer problem, and the second one fixes the race condition. So, this is the first one. These are the libraries I included, and these are the functions that I've declared. Inside my main, I have four variables: state, the buffer, and its size, the next in and the next out. Then I initialize my threads T1, T2, and T3. Each of these threads will execute these three functions in order, not in order, synchronously. There you go. And then after they finish, they'll be joined and the program will end. So let's start with what the print state function does. It basically prints the state every second, the OK state. The producer is a function that takes in the buffer size, and the next in variable. It will modify the next in variable. That's why it is a pointer here. So inside the function, it will execute a while loop. For each iteration, it will generate a random number between 1 and 8. Afterwards, it will um, produce data and store it inside the buffer. After the burst is done, it will move the next in pointer, not really a pointer, but it will move next into the last one after the last data that is added to the buffer. After that, it will generate a random number between 1 and 3, and it will sleep the thread for that long. My consumer, on the other hand, takes in the buffer, the size of the buffer, and the next out function. Inside the function, it will execute a while loop, and for each iteration, it will generate a random number between 1 and 3. It will sleep the thread for however that is. After it wakes up, it will generate a random number between 1 and 5. If you notice, uh, the the random number generator is different, the range. This is so that the race condition is more fair. From experimentation, if I put the random number range to be the same for the producer and the consumer, most of the time the consumer will win. Maybe because it relates to the buffer size. But anyways, I basically handicapped the consumer so that we'll have a fairer race. So it will generate K2. It will initialize a for loop from 0 to K2. It will access the buff. It will access the buffer, process the buffer, process the data inside the buffer, check whether or not there's a race condition. A race condition is found when data is greater than 1. That means the consumer is too slow and the producer has written to the same slot twice. If data is equal to 0, the consumer is too fast or the producer is too slow. Or else the buffer is consumed. Here you go, clear buffer slot. And then at the end of the for loop, it will move the next out pointer to the one after the last element to be accessed. And here is my function to generate a random number, a random integer. It takes a start and an end. It makes the random device object, which is used to seed the random number generator. It seeds the Mersenne twister random number generator. It also makes a uniform in distribution in order to make the range of the generated number between what we want, so between start and end. And yeah, it will call the random number generator and return it. So here's a bunch of execution that I made, that I ran. As you can see, producer is too slow for the first execution. Second execution ran for 5 seconds. The consumer is too slow. The third execution ran for 10 seconds, and the consumer is too slow. I can run this again, but now I will move on to explaining the modified version, the one that fixes the race condition by implementing semaphores. Oh, consumer is too slow again. Maybe I shouldn't have handicapped my consumer. Who knows? All right, so here is my modified. Here's my fix. So as you can see, there's more library included. We have mutex. I declared a semaphore class, and in there we have two operations: the p operation and the v operation. The p will decrement value if value is greater than 0, while value is greater than 0, and the v operation will increment value. Mutex right here will be used to make sure that value is not accessed by two threads at once. Aside from that, here are the four functions. The two producer and consumer functions are different in terms of their parameter list. As you can see, it's much bigger. Inside my main function, the same for the variable declaration. I have three extra variables: mutex. In this case, mutex is for the buffer, not for the value inside the semaphore. I have two semaphores, empty and full. Empty will have a value of buffer.size, so in this case 15. Full will have 0. And then I have my threads here, so 3 threads like the previous example, and I join them at the end and end the program. So since I fixed the race condition, I must end the program manually. So this is my condition to end the program. I want the program to run for 30 seconds before exiting. And right here, I made sure that the generated random number is the same for both producer and consumer. No handicap right here. Inside my producer, I execute a while loop, and for each iteration, generate a random number and initialize a for loop. What's different here is that I moved the next in the next in pointer inside the for loop. I also added the locks, the mutex locks, so that two threads won't be able to access the buffer at the same time. Empty dot p, it checks whether or not the buffer is full. If the buffer is full, it will wait. That means the producer will wait. If the value of empty is greater than 0, the producer is free to create data and add it to the buffer. At the end, after the producer adds the data, it will unlock the mutex, unlock the buffer, and it will signal to the consumer that the buffer is no longer empty. At least one slot is now filled. Okay, let's not get out of this for loop yet because we are executing this inside the for loop. Let's check our consumer here. Consumer is a function, and here is the definition. I execute a while loop, I sleep, and then I generate a random number after waking up. I initialize the for loop, and in here, I check whether or not the buffer is empty. So if full is 0, the consumer will not be able to consume anything. As such, it will lock itself right here if full is 0. If full is not 0, then the consumer will not wait. It will access the buffer by locking it, and then it will do the same check as in the previous example. After that, it will move the next out pointer, and it will signal the buffer to the producer. It will signal the producer. And in here, inside this one for loop, it will signal each other. As such, no race condition can occur because as soon as the buffer is full, the producer will not produce any more data. And the consumer is free to eat up as many as it likes. And then it will signal the producer again to produce data. So it does burst, but it bursts by going between each other after each while loop iteration. So between each burst, it will go back and forth with each other. As such, I don't think it will there will be a race condition. So here is my p operation for the semaphore. So while one, it locks the mutex. It locks value from being accessed by other threads. So in this case, empty.value or full.value. It checks whether value is greater than 0, and then it decrements it if that's the case, and it unlocks the mutex. Otherwise, it just unlocks the mutex, and other threads can access value. The V operation is very simple. It locks the value, it increments value, and then it unlocks it. Very, very simple. And my generate random int function is the same. So here we go. I ran this program twice, as you can see, and I ran them for 30 seconds each, and both of them finish without any race condition. Before this recording, I ran this program like 20 times, and it all ended up like this. I don't want to run it during recording because I do not want to wait for 30 seconds, and hopefully you do not also want to wait for 30 seconds. All right, thank you for watching, Professor. This is my presentation for the second project. I hope you understood what I'm going for with this. And yeah, thank you for watching.